1-1 in college algebra, refreshing our memory on the types of numbers. All we're talking about at the beginning is real numbers. You may remember from Algebra 2 imaginary numbers also, so they'll get to that later, but all we're talking about is real numbers. So let's kind of go through the basics. Here's a nice Venn diagram. The way I do it is I go from the smallest little circle to the biggest. Natural numbers. When they came up with numbers, it's the ones that were like natural in nature. Counting numbers. 1, 2, 3, 4. So those are our natural numbers. 1, 2, 3, and 4. And then that goes on forever. There's a symbol for natural numbers, which you will be held accountable for. The symbol for natural numbers looks like an N, but they have this little double bar right there. So that's what that blank's for. Natural numbers, the old double bar N. And this is way back in the day when they were coming up with numbers. Then all of a sudden they realized, hey man, there's other things. It's like if I had 3 apples and then I ate them all, where'd all the apples go? It's like, oh, how many apples do we have there? They didn't have the number 0, so they said we better create that. There are no more apples. So outside of natural numbers, there are whole numbers. So 0, oops, my bad, 0, and then all the rest of the naturals, 1, 2, 3, etc. Those are called whole numbers. It doesn't have a symbol. If you were taught to use a W, that's incorrect. We're going to do things correct. The real symbol for whole numbers is the integers greater than or equal to 0. Z is the integer, so that's a double bar Z. And it's all the integers greater than or equal to 0. Don't use W because that's incorrect. It was just something to help their little brains back in the day when you couldn't compute what the symbols were. Integers is all the whole numbers and their opposites. So you still got the 0, the 1, the 2, and the 3, but their opposites means you change the old sign. So the opposite of 1 is -1. The opposite of 2 is -2, and then that goes on forever also. And that symbol is the big Z. I call it double bar Z. So it's all the naturals and their opposites, like 1, 2, 3, and the opposites of those, and 0. You're cool with those 3, right? Rational numbers, just what it kind of sounds like. Rational has the word ratio in it. Ratio is like a fraction, so all rational numbers are integers over itself. If it can be rewritten as an integer over an integer, is 2 an integer? Yes or no? Yes. Is 3 an integer? See how I wrote them over themselves? It's a rational number. Any fraction or a terminating decimal. See, that's 0.5 right there, and it stopped. Terminating means it doesn't go on forever. Do you know what 0.5 is as a fraction? It's 1/2, like it can be written as a fraction, or even a repeating decimal. You know, like if it went on forever and you got the bar over it, like 0.3 repeating, isn't that 1/3, right? Any repeating decimal, any terminating decimal, or even just a fraction itself is called a rational number. Cool? So rational symbol is Q. The reason why I feel, I've never looked this up, but why I feel they use a Q, because of the word quotient. You know, quotient is like a fraction type deal, so Q, rational, Q, fraction. Thinking about, while we're talking about rational, I don't have a spot for irrational numbers, but irrational numbers are not rational numbers. Most popular one is pi. You've seen pi many times. It's 3.14159, blah, 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 blah. Why the blah, 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 blah? Because it's not a repeating decimal, it's not a terminating decimal, and I can't write it as a fraction. They had to make up a symbol for that number because it's irrational. Just like E also. Remember, E is some weird number. It's an irrational number. The square root of 2. Right? You punch the square root of 2 in, since that number is not a perfect square underneath there, you get a nasty decimal that has no pattern to it whatsoever. Square roots, not every square root, though, is an irrational number, because if I wrote that, the square root of 4, what's the square root of 4, really? It's a 2. See, isn't that number a perfect square underneath there? So no, 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 no. Just because I use the square root doesn't mean it's irrational. Square root of 3, though, is irrational, and etc. And then the real numbers, that's the double bar R. That's all the rationals and all the irrationals put together, right? They're real numbers. Then you also know about imaginary numbers. We'll deal with that later, right? So there's real numbers. That's what we are talking about. Little refresher on interval notation and graphing stuff. So they want us to graph this interval on the number line. It's all the numbers x. So this is one dimension, x, between -1 and 2. So this is like your lower boundary. This is your higher boundary right here. And let's just put them on the number line. -1, 0, 1, 2, 3. Doing a little graphing of this dude on the number line. Tell me about this -1. Included or not included? Included because of that equal to bar. You're very familiar with the open dots and the closed dots. You can use those. On my math lab, though, sometimes they don't have open dots and closed dots. They put the brackets and the parentheses instead. So do you remember which one meant it was included, the brackets or the parentheses? So what they might do, you might see it drawn like this, is they don't put a closed dot above -1, they put a bracket right there instead. I don't care if you use open dots or closed dots, it's up to you. I'm just telling you, when they have those on the screen, you know, it's like, what's this mean? It means that it's included, and the 2, isn't it also included, right? So that's a bracket. And then take a nice thickness and put it on the number line. Your teacher may have showed you to put that above the number line. I'm a person who likes to put it on the number line and put it nice and thick. Cool. Number 2, from 2 to 4, is the 2 included? Nope, and the 4 is not included, so instead of putting the dots, let's put the brackets and parentheses. We need a scale first, obviously, so start at 2, 3, 4, 5, 6. Always finish your scale. There's only 6 little dots there. I have 5, you have 6. Just finish it, you know. Finish what you started is always what I kind of believe in. 2 was not included, so that's a parenthesis. 4, oh, my bad. I didn't write the domain and range. And 4 was not included. And then we go inside of there, and I didn't finish the problem. It says graph each inequality, then write the solution in set builder and interval notation. So let's just start with number 2. Please label what you're doing. Number 2, I want to write this region in set notation. So start with the cool set bracket. It's the set of all x's. That's how you read that. If you've had me before, I've made you say that out loud before. So it's the set of all x's. Then you put this dude right here. Anybody remember what that means? Such that. Set of all x's, such that. And then you just basically rewrite this. And let me tell you how to read it out loud. That is honestly the hardest part and the #1 reason why kids fail college algebra is because they can't read it in the first place. Just gibberish. Set of all x's, such that. Then you always read from the variable first. X is greater than 2 and x is less than 4 is what that really says. Then in interval notation, so we'll do that underneath there, I just put int for interval notation. It's basically like your graph and this combo together. It went from 2, not included, to 4, not included. Right? This is nothing but parentheses. All right, let's do 3. From -2 to 3, -2, -1, 0, 1, 2. Uh-oh, you had an extra spot though, didn't you? You could make it. Were you able to make it from -2 to 3? Cool. Grapher, -2 does not count, so we put a bracket. 3 does count, so we put a, excuse me, -2 does not count, so we put a parenthesis. 3 does count, so we put a bracket, and then all the junk in between. In set notation, set of all x such that, and then you just kind of, I write it first and then say it after I write it. Set of all x's such that x is greater than -2 and x is less than or equal to 3. Number 4 only has one boundary, right? These first 3 were double inequalities or compound inequalities where there's a boundary on the left and a boundary on the right. You know, these over here only have one boundary, so we just need to put a 3. I like to put it in the middle, but then finish what I'm doing. 3 does count because of the equal to bar, so I will put a bracket. Since that's a greater than symbol, I'm making the bracket go in this direction, pointing to where my actual ray is going to be. Again, I don't care on your homework quiz next time if you use dots and or open dots and closed dots, or if you use brackets and parentheses. It's up to you, right? If it's right, I will count it right. And if it's wrong, I will count it wrong. X less than 5, I need a 5 in the middle. 6, 7, 4, 3. 5 does not count because there's no equal to bar. And going to the left, to the left, to the left. I didn't do the set and interval notation again, my bad. So let's do set. this guy. Set of all x's such that x is less than 5. Again, the set notation is pretty much given to you in set notation already. You just got to put the set of all x's such that in the set brackets. And then the interval notation, that's where you read the actual drawing that you made. It's like you always read from left to right. How far to the left did my green arrow go? From negative infinity to 5 not included. We went from negative infinity to 5. Just reading this guy from left to right. It went all the way to negative infinity to 5 not included. All real numbers, got to graph it. Like what should you put down here? Anything you want to. 1, 2, 3, 4, my bad, 0 and negative 1. Got to graph them all. Well, you graph them all. So you fill the whole stinking thing in. And it goes on forever and ever. Let's see how good we are at remembering how to write that in set notation, though. Set of all x such that. That always starts with it. Then, aren't they all the real numbers? So x is an element of, that's like kind of looks like an E. Let me draw that again for you. I always make a C and then put a little dude in there. Kind of looks like the letter E. Is an element of the real numbers. What symbol is real numbers? The double bar R. And then close your bracket off. Set of all x such that x is an element of the reals. The more you say it to yourself correctly, the more better you will do. More better, yes. Simple. Next, examples of polynomials. Why don't you write those down while I kind of explain it? Make yourself a little room in that spot that's blank right there. You can have examples and not examples, or polynomials and not polynomials. But a polynomial is an algebraic expression containing a finite number of additions. Finite means you can count it. Infinite means you can't count it, right? Finite means you can count it. A finite number of additions, subtractions, and multiplications of constants, non-negative integer powers, and variables. When simplified, a polynomial cannot contain negative powers of variables, fractional powers of variables, and variables in a denominator or variables inside a radical. This is the most important part of all that stuff. Tells you what you can't have. Says you can't have any negative exponents. You can't have any fractional powers, like fractions for an exponent. You can't have any variables in the denominator, and you can't have any variables inside a radical. If you look at all of these are examples. These work, right? There are no negative exponents. There are no fractional exponents. There's no exponents in a radical. There's no exponents in the denominator. Good. That's not a fraction, nor is it negative. Good, 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 good. Examples of not polynomials. These are things you would probably want to write down. What's not a polynomial? Let's see here. Why is this brother not a polynomial? What's bad about him? Got a variable downstairs. Can't have it, right? Because you also should know that if you had like this, 1 over x, isn't there a variable downstairs? That's the same thing as x to the negative first. It's got a negative exponent also, right? So not good. This is not good right here because it's the square root of x. It could also be written as x to the 1/2, which is bad because you have a fraction for an exponent, fractional exponent, and this is a negative exponent, which really means that that's really like 3 over x squared, which is a variable in the denominator. Can't have it, right? So not polynomials. Things they ask you. I think I typed all this stuff out for you so we don't have to write it, right? Yay for me. I'm a good typer. Consider this polynomial. I don't know if that's written at the top either. You might want to write that down if it's not. If we got this guy right here, the degree, if you've got a polynomial in the single variable of x, that means the only variable in that polynomial is x. There's no y's or z's or any of that junk. The power of x in each term is the degree for that term. Remember, terms are separated by addition, subtraction, and equal signs. So here's an addition sign. There's a subtraction sign. Doesn't that have 3 terms in it? If this is all in x, if you look at the exponent in each term, this guy has degree 4, this guy has degree 2, and this guy has degree 0 because there are no x's right there at all. So they want to know what the degree of the whole polynomial is. It's the biggest one of those degrees, which is 4. Right? So this guy has degree 4. The leading term is 5x to the 4th in this guy. the term with the highest degree. So this is our leading term. This is written in what's called standard form right here because it's from highest degree to lowest degree. So the leading term in this guy is 5x to the fourth. The leading coefficient is the number in front of the variable, so that's 5 in this particular guy. And then a monomial, a binomial, a trinomial, 1 term, 2 terms, or 3 terms. If they have 4 or more terms, it doesn't have a fancy name. Just those 3 guys, monomial, binomial, trinomial. So let's go through this. This has 4 terms. The constant term is the dude that's got degree 0. It doesn't vary. It has no variable with it. It is constant. That's this guy. Man, this thing is really jumpy today. -3 is the constant term. What's the leading coefficient? A lot of people would boo-boo and put 5, you know, because that's the dude that leads off. This has to be written in standard form first. So the leading coefficient, you better put it from highest degree to lowest degree. I don't care if you rewrite it or not rewrite it, but doesn't this guy right here have the biggest degree out of all of those, right? That's the 4th degree. If you want to rewrite it, it would go 2x to the 4th plus 5x squared minus 8x minus 3. That's in standard form, each highest degree to lowest degree. The leading coefficient is a 2, and the degree of this polynomial is a 4, whatever the degree of that guy is. Cool? How about this guy? What's the constant term? You can help me. What's the constant term? 7. Leading coefficient? Well, I'm just going to circle the dude with the biggest degree. Isn't that guy right there? So what's our leading coefficient? 3. And the degree is 6. Yay. I also have all this stuff defined for you. A function. A function is a correspondent in which every element in the domain maps to exactly one element in the range. That is something you should probably know, because when they ask you why on a lot of things, you kind of have to restate that definition. Every element in the domain maps to exactly one element in the range, and I'll show you some examples here in a second. And functions can be many things. They can be ordered pairs, which are called relations. I'll show you a visual of that. A table of values, a mapping, or a graph. Domain and range. The domain is like the set of all possible x values, if you need to write that down. And the range is the set of all the possible y values. Oh, my bad. Why did that go over? Domain is the set of all the possible x values, and the range is the set of all the possible y values. Again, nothing you haven't seen before. You just might not remember it that well. You know, none of this should be new to you. Domain, set of all the x's. The range is the set of all the y's. Domain is independent, and range depends on domain. Y depended on what x was. Right? If I wanted to know what y was, I need to know x first. Right? Y depends on x. So here's some visuals. You don't have to draw any of this, but a relation is just a set of ordered pairs. These over here are functions because every element in the domain, which ones are the domain? The x's or the y's? X's, maps to exactly one element in the range. See, 1 goes to 2. There's a 1 there, there's a 2 there, and there's a 3 there. Easy way to look at it is nothing ever repeats itself. I don't see 1 more than once in the domain. I don't see 2 more than once in the domain. I don't see 3. 1 goes to 2, 2 goes to 4, and 3 goes to 6. Here, 4 goes to 4, 5 goes to 4, and 6 goes to 4. Even though in the y values it's always 4, 4, 4, look at your x values. Did you see any quote-unquote repeaters in there? No. Look at this, not a function, no. They'll ask you on the homework, you know, is this a function or not a function? You say yes or no. If no, explain why. Why is that relation not a function? So here's what we'll write. Oh, I guess you don't have this. You'll say the element 2 in the domain maps to more than one element in the range. I'll let you write that down if you want to. The element blank, whichever number was the problem, wasn't 2 the problem guy in this one. The element blank maps to more than one element in the range. The element whatever, in this case it's 2, maps to more than one element in the range. You can also see it as a table of values. That's how a function can be defined or not defined. Look at all your x's. Any repeaters in the x's? Don't see the same number twice. It's an easy way to say that that's a function right there. Over here, you see any numbers twice in the x's? You got a -1. You better look, though, to see if they map to different things. Do they map to different things? So you'd say the element -1 in the domain maps to more than one element in the range. And then when you see a mapping, that's where they put that cool little bubble. Your domain's over here. Your range is over there. Very simple. The arrow, only one arrow coming off of this guy. Only one arrow, only one arrow, only one arrow. That means that's a function because 2 maps straight to 3, 5 maps straight to 4, and etc. If you look over here, one arrow, one arrow, one arrow, one arrow. Even though both of these guys are going to 6, right? 3 goes to 6, 4 goes to 6. One arrow coming off of these guys. But look at him. How many arrows coming off of 8 on that bad boy? More than one, right? So 8 maps to 6, and it also maps to 9. Bad deal. The element 8 in the domain maps to more than one element in the range. If you have a graph, oh wait, they just want to know the domain and range of this in both set and interval notation. So domain, let's do this first. Let's label it like so. Let's do set notation first. Domain, I just put a D. Set of all what? What variable do you use? X's, such that. Read your graph from left to right. Domain is x values, which is your x-axis. X-axis goes from left to right. If you follow this guy with my blue highlighter, how far to the left will that highlighter end up going? -infinity, and how far to the right will my blue highlighter go? Even though it went up, how far to the right will it go? Positive. It goes from -infinity to positive infinity, right? That's interval notation. We want it in set notation. What numbers work for x? All the real numbers. So how do I write it in set notation? Set of all x such that x is an element of the real number system. All real numbers work for the domain. Range is your y's, low to high. Always start low to high, right? You want to go small to big, right? Reading from left to right. How low does this bad boy go on the y-axis? To 0, so it's a set of all y's such that. Does 0 count or not? That's the real question. Well, if you kind of erase all this stuff here, there's no open circles at 0 right there. It's not an open dot. It's a closed dot. It's filled in, so 0 counts. If there's a hole in the graph, you'll see that they'll put an open dot there. So 0 counts, so it's all the y values that are greater than or equal to 0. Because doesn't it go from 0 is the lowest, and it goes up to positive infinity. Always go low to high on range. Now let's put that in interval notation. The reason why we're doing all this is because that MathXL, or my math lab, will ask you all these different questions. And you remember how picky it was back in the day? It's like, oh, I didn't type it in right, you know. Did they want it in set notation? Did they want it in interval notation? You have to read the instructions. So interval notation, the domain, from -infinity to positive infinity. Never put brackets with infinity because you can't reach it, right? It's always parentheses with infinity. And then the range, low to high, 0 counted, so we put a bracket. And he went all the way up to infinita. So set and interval notation. Rock and roll. Next guy. Nice little hyperbola. We were not very familiar with those, but they have asymptotes involved with these bad boys. Numbers that don't work. You should know the basic rule that you can't divide by 0. You see how there's x down in the denominator, correct? What number will make the denominator 0, baby? If x was 2, we'd have an impossible situation, correct? We'd have 1 over 0. So we know, write this off to the side, that x can equal 2. If x was 3, we'd be good. If x was 1,000,000, we'd be good. But x can't be 2 because that makes that denominator a 0. You should also realize that this, if you divide by a positive number, you will get a positive answer. If you divide 1 by a negative number, you will get a negative answer. But 1 divided by something can never turn out to be 0. So the y value will never be 0. And if you add 1 to it, y can't equal 1. Since this dude right here can never turn out to be 0, think of it as 0. If this was 0 and you add 1 to it, then you'd get 1. Y will never turn out to be 1 because this will never ever be 0, right? And 0 plus 1 turns out to be that. You can see it on the graph too. Remember those asymptotes right here? There's y equals 1. Remember y is a horizontal line. and that's right there at 1, and x equals 2, that's an asymptote. This graph will approach it, but never, ever, ever touch it. So let's do the easy one first. Let's do interval notation on domain. Look from left to right. I'm a highlighter guy. Those of you that had me back in geometry especially, I highlight everything, right? If I want to see domain, domain is from left to right. Well, these two branches here is what you got to follow. How far to the left will that thing go? How far to the left? So I'm reading from left to right. I'm starting at negative infinity. Then I'm going to keep working my way over here. And then all of a sudden, this thing's never going to touch what? Never going to go where? To 2. So I'm going to go from negative infinity to 2 with a pen. With a pen. With a pen. 2. Ah. Kidding me? Killing me, Smalls. To 2. The 2 count. The 2 count? No. Then we unite that because there's more to it. It starts over again at 2, not included. And then how far to the right will that thing go? To infinity. Just reading it from left to right, you went from negative infinity all the way to 2. Then you got to do a little union because there's a whole other branch from 2 to infinity. Range, low to high. How low does this thing go? From negative infinity, and then it'll go all the way up to where? Where's this critical point at? At 1. It'll never reach 1, so it's not included. Then you unite that. It will continue to start over again at 1, but not included, and then go all the way up to infinity. Yeah? Interval notation, that's what interval notation was designed for right there, to make all these different branches easier to read. Putting it in set notation, hi-yi-yi, that's why we invented interval notation, but let's see it in set notation. The domain, set of all x's, such that. Can you figure out what this means right here? X is less than 2. Isn't that what that means right there? All the x's is less than 2. Union, this union greater than or. I don't know if you remember that phrase. Union means or. X is what? Greater than 2. Think about it. What didn't work for x? 2. Everything but 2. Another way to write that, if you wanted to, set of all x's such that x is an element of the reals not equal to 2. Right? If such that x is a real number that's not equal to 2. It's another way to write the same thing. Range, set of all y's such that this dude right here says y's got to be less than 1, or y's got to be greater than 1. Yep. Give 11, well, I'll do it for you. This is college algebra. Let's try this one. Domain in set notation. Set of all x's such that. This is basically my critical point right here. Reading from left to right, how far left will that graph go? From negative infinity. So all the x's are like less than 4, correct? Does 4 count? Did they put like a nice, if it didn't count, you'd see an open circle right there. Right? You don't see that, correct? So does 4 count, yes or no? 4 counts. So x has got to be less than or equal to 4. All the x values on that thing are either 4 or less than 4. Cool? How about the range on that bad boy? Think of it low to high. Set of all y's such that. How low does that little graph go on the y-axis? How low? 0. And it counts, right? And then it always goes higher than that also, correct? So if you want to say y is greater than 0, y is less than 0. Y is greater than or equal to, because it counted, 0. Write them in interval notation also. Interval. The domain. My bad. From 0 included to infinity. And I would say 99.9% of the time interval notation is much better than set notation, but we'll come across some problems why you have to use set notation. Yep. Function. You can also tell if something's a function by using the vertical line test, but the only thing you can do the vertical line test with is a graph, correct? So, graphing calculator time. All right, so what we'll do is we'll actually just graph it on our calculator. You go to y equals, clear all that stuff out, negative x squared plus 4x. I know you've already graphed it. Can you preview it and realize in the brain that it's like a parabola? Because what's the highest degree that you see right there? 2. Zoom 6 is how you get to that standard window. And what I ask you to do is make a little sketch of it for me right here, right? On your actual paper, just sketch. If you want to be a straight edge person, all good. If you have horrible handwriting, get yourself a straight edge and just rough sketch. Something that looks like that. I don't need any points on there because I really don't care about that. They're asking me, is this a function or not? So I require you to just make a little sketch of what you made, and then you use the vertical line test. If you draw a vertical line through this, if it intersects it in only one place, every single time, it's a function. Is this a function, yes or no? So, yes. Why? Graph, that's the most important word. Not it passes, the graph passes the VLT. What's VLT stand for? Vertical line test, right? The graph passes the vertical line test. Cool? If we want to do number 13 on our graphing calculator, there's a major problem with that because look at your graphing calculator. How do you type stuff in your graphing calculator? What's always all by itself on the left side? Y to the first power. This is y to the second power, correct? So we got to solve for y. And how do you get rid of this square right here, baby? You square root. And you should know that when you square root, you get a plus and a minus answer, correct? Square root of 4 is either 2 or negative 2, correct? So what you got is you've got two different situations. Let's write this down so you can see what you punched in your calculator. You got y1. Why did I call it y1? Because that's where we're going to put him in our graphing calculator. y1 could equal the square root of 3x minus 3. Right? Didn't I just square root both sides? Right? And y2 will equal almost the exact same thing, but it's the negative square root of 3x minus 3. Because you got the plus or the minus when you solved it, correct? And you got to graph both things. So we go into here, and you want to type in the square root of, and it automatically puts that parenthesis there for you when you're punching them in. You want to do 3x minus a shwi, close that parenthesis up. Then you go down here. Make sure you hit the negative, not the subtraction. Right? You want to hit negative square root of 3x minus 3. And you may have already hit graph, but I want to show you something. Kind of watch mine if you've already hit graph. When I hit graph, since there's two different equations graphed there, it will graph the first one first, and then you'll see the second one start. Okay? So watch. See the first one? Oh, I hit graph first. See the first one? Boom. Half a parabola. Boom. The second one started. It was the other half of the parabola right there. This is called what we call the sideways parabola, if you will. It's the inverse of that the quadratic function. So a sketch is something like so. There was the first half. That's the positive version in red right there. And then there was the second half. Just trying to explain it to where you kind of understand what happened. You know, if this was college, the question is it a function or not? You see that graph? Is this a function or not? Yes or no? No, because check that out. Why is it not a function? Didn't pass the VLT, right? So no, the graph, I just say fails the VLT. Let's see. If I put 4 in for x, let's say x equals 4, right? If I put 4 in for x, what's 3 times 4? 12. Take away 3. So you got y squared equals 9, right? If x equals 4, y squared equals 9, correct? Then what could y equal? y equals plus or minus 3. Don't you get two different answers right there? If x was 4, you get y being 3. You could also have the point 4, negative 3. The element 4 in the domain mapped to more than one element in a range. Yeah, functions. If you have a graph, please sketch it for me and then see if it passes the vertical line test. Boom. Over here, consider this function. Big boy right there. What's his degree? Degree 3. Cubic. Remember the snake dude right there? Cubic. Real simple questions. Use the points shown on the graph. Math Excel, I keep calling it Math Excel. It's my math lab. My math lab will ask you, please use the graph, and they'll have it graphed for you already, to evaluate f of negative 2 and f of 4. This is the x value right here. So f of negative 2 says go to negative 2 on the x-axis. Right here. And you see they've actually listed for you the ordered pair right there, correct? What is the function evaluated at negative 2? They're saying, what would y be if x was negative 2? What would y be if x was negative 2? What do you get? 45. So you'll answer it. There's not really room, so part A right here, f of negative 2 equals 45. And then they ask you to evaluate the function at 4. Well, by God, they put it right there for me. The function evaluated at 4 is how much? So that's Euler's notation stuff again. We'll even ask you sometimes to do it by hand, because that's what part B asks you to do right there. And the homework quiz next time will ask you to do this by hand also. So let's do that. Hey, should you know what the answer should be already? Don't they ask you the same questions again? We better get 45 for the first answer, and we better get 81 for the second answer. But when they ask you to use the equation, I know how my math lab works. I don't check any work. You could backway yourself into the answer and just punch it in. But when you take the homework quiz the next period, I want to see the work. Does that make sense? So let's substitute in. F of negative 2 equals 2 times negative 2 cubed plus 5 times negative 2 squared minus 28 x times negative 2, my bad, minus 15. You can use your calculator. Like, I'm not against it, you know, not against using your calculator. You already know that the answer better turn out to be 45. So f of negative 2 equals, I don't really like to punch that whole thing in, you know, show me a little bit of work, but let's punch this in. 2 times negative 2 cubed, you could punch it straight in like this if you get out of here. Remember, to get out of your graph, you just hit second quit, right? So 2 times negative 2 to the third. That term turned out to be a negative 16. And then figure out what each individual term is after it. There'll be very little of this kind of stuff, you know, but just freshen our algebra skills. What's negative 2 squared? 4 or negative 4? Negative 2 squared is 4 times 5, which is 20. And then negative 28 times negative 2 is positive 56. Minus 15. Then you just punch all that stuff in. We'll do a lot of graphing calculator stuff, but if a question asks you to specifically show, if it asks you to show some algebra, please show some algebra. And then f of negative 2, punch all that in, you get 45. Same thing with 81, right? They'll also ask you eventually to find all the turning points, right? A turning point, let me erase all this stuff, is where the graph goes from increasing to decreasing. We didn't talk a lot about that in Algebra 2. You do that at FST, probably know all about it. But where it goes from increasing to decreasing, follow my highlighter. Is that thing going up or down? Up, 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 up. Uh-oh! Now what happens to it? Goes down. It happened right there, correct? That's a turning point, where it went from increasing to decreasing. Use your graphing calculator to find it. Okay, so let's punch that equation into our graphing calculator, that function. Clear all this other stuff out. Slow down when I ask you something. Remember how the window was a hard thing to figure out? It's like, what's my window going to be? Well, by gosh, do you think we could figure out what the window would be when all the scale is labeled for us already there also? So first I'm going to type that dude in. 2x cubed, right? Plus 5x squared minus 28x minus 15. I always double check, make sure I typed it in right. Change my window. X's can be from what the standard window is. It just went 6 to all this. So going from 10 to negative 10 is all good. But the Y's, right, you need to change. So I'm going to set my Y scale. The Y minimum was at negative 40. Y max is at 140. And I'm going to change the scale. Instead of counting by ones, I'm going to make it count by 20s, just like that graph is. They're counting by 20s. That's what Y scale is right there, counting by 20s. Then I hit the graph. Should look the same, better look the same. I'm looking for this dude right here. You tell me, minimum or maximum, what happens right there? Is that graph a minimum or a maximum? So second calculate. We want to choose the maximum option, which is 4. Then you got to set your cursor over there. You need to go to the left of it first, so you got to move that dude all the way over. Somewhere to the left of it, hit equals. Somewhere to the right of it, hit equals. Ask you to guess, just hit equals one more time, and boom. Not very nice, so round it however they ask you to round on MyMathLab, you know, but there it is. My turning point, one of them's at about negative 3 point, what was it? About 1 comma 60 point something or other, 60.3. And then you find that other one. So there was one of my turning points, right, where I went from a minimum to a maximum. It also works the other way around, where it goes from a maximum to a minimum, or decreasing to increasing, or increasing to decreasing, my bad. A turning point where it goes increasing to decreasing, or vice versa. Isn't this dude right here another turning point right there? So you find him by second calculate, and you can get him down. Let me know if you have any questions. Have a good one.